hear us? In the Renater?
Yes.
But in the Renater, no, right?
No. No.
Hello, do you hear us?
Yeah, I hear you.
Perfect. Good to see you.
Yeah.
Would you like to speak? Yes. Can you speak? I'm not with this one.
Yeah, I can speak. Do you hear me correctly? Yeah, I don't know if the micro is on. Okay.
Yeah, okay, that's perfect.
Cool. Nice. Okay, then if it works. Switching anything?
But you can...
I'm going back. Put it down.
toi, tu les vois en face de toi, normalement,
Quand ils apparaissent, je les
Ouais.
vois. Mais je pense qu'il suffit qu'à désactiver la caméra. Je vais juste voir sur le mail, voir si je n'ai rien dit.
Là, ce serait, oui, au moins que au démarrage de la soutenance, on se voit tous.
Oui.
Ça.
How are you feeling?
Feels not good.
Here they are.
Ah, il est là, à côté.
Oui. Mais tu peux activer le micro et lui parler pour qu'il regarde.
Well, I let you introduce the members of the committee, and I hope we're all here.
Okay, can you hear me? I'm sorry to be kept on the phone. Is it okay from your side?
We do hear you.
Okay.
But let me just check. Sorry, do the other members of the jury hear you?
Yes, perfectly.
Okay.
Perfectly. Okay, so again, sorry for being on the phone like this. It's my great pleasure to launch this strategic committee. So my name is Andrea Mendizabal. I am a senior researcher at the University of Alp, and I have been appointed to chair this committee. So I've had the pleasure of following Andrea's thesis work since I participated in her what we call in French PhD individual monitoring committee. And I have therefore been able to see all the progress made since she started this research work. So the committee will include today four other colleagues. So the first reviewer is Professor Elias Cueto from the Universidad de Zaragoza. The second reviewer is the Professor José Martín Guerrero from the Intelligent Data Analysis Laboratory of the Universidad de Valencia in Spain too. Third member of the committee is Sufik Chakraborty, who is an assistant professor at the Department of Applied Mechanics in the DB Indian Institute of Technology. And finally, Stéphane Coffin, who is an in-area researcher from Strasbourg University, and who is here as the supervisor of this PhD work. So, Andrea, the microphone is yours for around 45 minutes. Thank you.
Thank you very much for the introduction. So, I hope you can hear me well and see correctly the slides. No? Yeah, okay. Perfect. So in today's presentation, we will see how combining deep learning techniques with numerical simulation can help in medical applications. So here is a general overview of the presentation. I will first introduce the medical context. Then I will present the main contribution of this thesis work, that is the UMesh framework, and the applications to this framework to anatomical structures, and in particular to hepatic surgery. To finish, I propose a perspective section where I will present some techniques to generalize the proposed networks. In the medical field, there are plenty of applications requiring numerical simulations, going from surgical training to intraoperative guidance with augmented reality. In such simulations, several quantities may come into play, such as the temperature in cryotherapy planning or the electrical response of tissues in neurosurgery. But in today's presentation, we will focus on modeling the tissue's deformation, which is a common challenge to all these applications. Indeed, during a surgery, for instance, the tissues may deform due to, everything is okay? Okay. So the tissues may deform due to the interactions with the surrounding anatomy or to surgical manipulations. So in order to model such deformations, several works have proposed the benefits of using physics-based models, and in particular the finite element method. So the FEM produces an approximation of a partial derivative differential equation, by discretizing a domain with nodes connected by elements. So here I show the partial differential equation we aim at solving. It describes the equilibrium between internal forces and external forces, And instead of integrating the equation over the entire domain omega, we will use the finite element discretization. The first term of this equation describes the relation between the stresses and the strains, namely the constitutive equation, and also the material properties. In the second term, we can see the boundary conditions. In particular, Neumann boundary conditions are applied on gamma n and consist in surface forces. And Dirichlet boundary conditions are applied on gamma d that represent the fixed areas of the boundary. In our case, ud is equal to 0. The last term represents the volume forces, such as gravity, for instance. So there are many ways to discretize a domain. The most common approach is to use 4-node tetrahedral elements because they are fast and easy to generate, but they have bad numerical properties. So for this reason, we will prefer using 8-node hexahedral elements, known for their good convergency and stability. There are two main sources of computation burden in the FEM. First of all, the mesh resolution, and second of all, the nonlinearity of the constitutive equations. So, bad luck, when modeling soft tissues, these two aspects are present. Indeed, when modeling big organs like the liver or the heart, the simulations must produce an error below 1 millimeter, which is equivalent to the resolution of the medical images, meaning that we need very fine meshes for our simulations. Also, most soft tissues exhibit a hyperelastic behavior, so we need to include nonlinearity in the equations. All of that makes it really challenging to achieve real-time simulations with the standard finite element method. For this reason, many authors, and some of them are members of the jury, have proposed methods for accelerating the computations of the FEM. For example, we can use a GPU, and it considerably accelerates the computations as long as the code is parallelizable, which is not always the case, and as long as the GPU is available, of course. Another alternative is to use domain decomposition that, under certain conditions, can achieve superlinear speedups, but for relatively small problems and for real-time applications, the speedup is very limited. Another option is to reduce the number of degrees of freedom of the model by using model order reduction techniques, such as proper orthogonal decomposition. It computes offline the numerical solution to several complete problems called the snapshot, and it extracts the principal deformation modes in order to compute the reduced solution. The main limitation of this approach is that it is not suited for material nonlinearity. Of course, this list is not exhaustive. There are many other numerical methods that can be used to accelerate the FEM computations, and one may choose one or another depending on the size of the problem and on the targeted application. But in general, we may say that even if all these approaches are well established and present good performances for complex constitutive models that take into account patient-specific properties, the speedups are still limited. For this reason, we decided to look into machine learning for solving elasticity partial differential equations. When we started this PhD, there were only very few papers, which proves the novelty of the approach. But still, there were some references. And basically, there were two main approaches. Either we used data-driven neural networks or physics-informed neural networks. In data-driven neural networks, usually simulated data is used to train the networks in order to make it learn the equations of the elasticity equations. The problem with these approaches is the expensive data generation process. The other option is physics-informed neural networks that encode the elasticity equations and the initial and boundary conditions directly in the loss function of the network. The problem with these approaches is that the exact physics must be known in advance, which is not always the case in our problems. And it is not clear to us how these methods could adapt to new boundary conditions, for example, because they are hard-coded in the laws. So let me introduce the problem we aim at solving. Assume we are given a domain omega whose geometry is known. It can be the surface of an organ, for instance. We also have an a priori knowledge on the constitutive equation of the object, but we do not know the elasticity parameters. Also, the Dirichlet boundary conditions are known in average, but on the contrary, Neumann boundary conditions are not known in advance, meaning that we don't know how many forces will be applied, and we also don't know their location. So the objective is to build a generic deep neural network that is capable of predicting accurately the solution to any combination of this set of problems. Now the question is how to choose such a network architecture. Well, we want to estimate displacements, so we should use a regressor instead of a classifier. Also, we would like our network to be rotation and translation invariant, meaning that we should use convolutional layers. And the objective is to learn a representation of the data by extracting principal features such as deformation modes. So we would like to do like in reference 13, where they use a deep autoencoder with fully connected layers, and they compare it to principal component analysis for very similar problems. But our proposal is to use a deep autoencoder for its similarities with model order reduction, and include convolutional layers. So this is basically a unit architecture. And this is where we come to the presentation of the UMesh framework. So it consists, as I said, of a unit architecture that is a fully convolutional neural network that was initially built for image segmentation. It has an encoding path that transforms the input to reduced space, and a decoding path that expands it back to the original size. Intuitively, each convolution kernel learns to isolate the different characteristics of the displacement. So in order to train such a network, we want to minimize the difference between the network prediction h of fn and the ground truth un over the set of parameters of the network. And in order to compute this error, we wanted to use a geometrical loss. So we chose the mean squared error loss. F of n is the input tensor that can be a contact force, for instance, and un is the output tensor, that is the ground truth displacement. As we have seen, the unit has convolutional layers, and CNNs were designed to work with images, meaning regular grids. So there is an emerging approach that proposes to use graph CNNs for geometrical deep learning, but this is a still too young approach to be used due to some performance issues. So basically we will use regular grids, and for that we had two options. Either we directly use a regular hexahedral mesh for the finite element simulation, which directly matches the regular grid structure, or we embed the tetrahedral mesh in a regular grid. So we tried the two options, but for the sake of clarity of the presentation and of accuracy, we'll stick to the first one. So the input tensor f of n and the output un must be encoded in a 3D grid of the desired dimension. Okay, so the minimization is performed over a training data set of n samples generated with the FEM. In order to generate such data, we assume we are given a 3D mesh with hexahedral elements, a hyperelastic constitutive model like the Saint-Venant-Kirchhoff model, material properties, and Dirichlet boundary conditions. Neumann boundary conditions are not known in advance. We don't know how many forces we will apply. So we will generate random forces at random locations of the surface. So here is like an algorithm of the data generation and network training processes. So in order to generate an optimal data set, we propose to uniformly sample a sphere, both in direction and in amplitude, in order to generate a set of force vectors. Then we select random forces and apply them to a set of random surface nodes. The obtained system of equations is solved using the FEM, and if the solver converged, we store this sample as an element of the dataset. And so we repeat this process until we generated the desired number of samples equal to capital N, and then we can train the network for the desired number of epochs. So roughly 40% of this process is spent in the data generation, and 60% is spent in the training of the network. So this is how it looks like. We will generate various deformations of the considered object in order to train the network such that from an input force it can predict the corresponding volumetric displacement. And the prediction is compared to the finite element ground truth solution by using the MSE loss. And this loss in order to update the weights of the network. So we have seen that we need regular grids to make the process work. So we propose first some results on regular geometries. Let me first introduce the metrics we will be using in the following. So we have a testing data set containing M samples, and we will compute some metrics over that data set. So there are various possible norms here. The objective is to compare the network's prediction to the ground truth displacement and note that this norm doesn't need to be the same one as the one used in the training loss. Moreover, if they are independent, we avoid introducing any bias. So we decided to compute what we call the mean norm error of each sample. That is basically the average nodal L1 norm. We compute also the average and the standard deviation of such norm over the entire testing dataset. So here, first results on a cantilever beam. In green, I show the UMesh prediction, and in blue, the reference FEM solution. The red arrows correspond to the input forces. And, well, we can see that we have a pretty good visual agreement between the two. Indeed, this is a 4-meter beam, and we induced deformations up to 1 meter. And the average mean norm error is smaller than 1 millimeter. Also, the prediction time is equal to 3 milliseconds, which is extremely fast. One important point here is that the UMesh works for any number of input forces, actually. We also tried it on a finer beam, and the interesting result here is that the prediction time is constant and equal to 3 milliseconds. The prediction time is still equal to 3 milliseconds, meaning that it's constant regardless of the resolution of the grid, which is really not a property that the FEM has. We also applied the UMesh to large deformations on an L-shaped object, and again we achieved interesting performances and a prediction time of 3 milliseconds. So we wanted to compare the method to a previously existing method, and we chose the proper orthogonal decomposition for its similarities with the unit, and we computed we compared the two methods for a given error. So the scenario we are considering is the cantilever beam, where we pulled in the tip of the beam, in a node of the tip of the beam. So the error we achieved with the two methods is equal to 6 millimeters, and in order to achieve such an error, we needed to keep 3 modes with the proper orthogonal decomposition, which led to prediction times about 40 times bigger than the prediction time needed for the U-mesh. We also compared the 2 methods for a given computation time around 5 or 3 milliseconds, and to achieve such a fast prediction with the proper orthogonal decomposition, we needed to use the hyper-reduced POD and only keep 1 mode, 1 deformation mode, which led to pretty big errors actually. So let me summarize what we've done till here. We have a method that predicts a displacement in a constant amount of time up to a certain grid resolution. It produces small errors, even for large deformations, even for large displacements, sorry. And it works for a variable number of input forces. This is an important characteristic, as we have seen it was one of our requirements. It also performs better than the POD, and for now we have shown results on regular geometries. What happens now if we want to apply it to a non-regular geometry, like an anatomical structure, for instance? To see that point, we propose to consider well-characterized problem on a phantom setup. So this is a joint project with the University of Verona in Italy, and it deals with ultrasound-guided breast biopsy. So correctly placing the lesions in while doing the procedure is a challenging task, because the lesions are not always visible in the ultrasound images, and due to the poor contrast of the ultrasound, and also the 3D navigation is performed based on 2D images. So our objective would be to track the position of the ultrasound invisible lesions that were previously identified on a preoperative CT scan, accounting for the probe-induced deformation that can be really high. So we want to account for this deformation by using the U-mesh. But the question we need to answer first is how to encode the displacement into a regular grid. So we propose to embed the organ geometry, in this case the green sphere, into a regular grid. The cells that are inside the domain and those overlapping the boundary are kept in order to build a sparse grid discretization. And we combine it to an immersed boundary method that allows for the use of regular hexahedral meshes for accurate simulations. In the image on the right, I show the sparse grid for the breast that we will be using in the following. So an important point here is that the input to the network will be the displacement of the nodes that are under the breast probe contact area, so the red points in the image. This means that no patient-specific parametrization of the model is needed, because the relation between the surface and the volume displacement is independent of the stiffness of the material, at least for homogeneous materials. And this is a very important property of our method. For the constitutive model, we chose the hyperelastic Saint-Venant-Kirchhoff model, and we fixed the base of the breast just like in our phantom data. So in order to train the network, we generated random probe-induced displacements, and the network learns to predict from a sparse input point cloud the complete volumetric deformation. So overall, the data generation and the training of the network took less than 5 hours. Once the network is trained, we assess its performance on a synthetic dataset. In green, I showed the U-mesh prediction, and in red, the ground truth FEM solution. So the first sample is the sample with maximal error, and the sample in the middle is the one with largest deformation. So we can see that we have average errors that are smaller than equal to 0.05 millimeters, and the prediction times are close to 3 milliseconds again. In order to validate our dataset, our training on real data, we chose a phantom data. And in the experiments, we extracted the ground truth positions of the lesions from the ultrasound images, and we induced several deformations of increasing extent with the ultrasound probe on the surface of the breast. So these surface deformations are given to the unit so that it predicts the complete volumetric deformation. And we compute target registration errors between the unit predicted position of each lesion and the ground truth of each lesion. If we compare the UMesh with the FEM, we reach similar accuracies, in average 4.2 millimeters of target registration error. But we have a real computation gain when using the UMesh. So if I summarize, for a well-characterized problem, meaning that the Dirichlet boundary conditions are exactly known and that there is no noise in the input to the network, the UMesh produces an error that is equivalent to the FE model used to train it, and while being 100 times faster. Also, since we have a displacement as input, no patient-specific parametrization of the model is needed. And in order to account for non-regular geometries, we propose the immersed boundary method. Now, what happens if we want to consider a more complex scenario with noise, etc., like building an augmented view of liver surgery? So let me first explain how we usually do it. So before the surgery, we build a preoperative model of the organ using the segmentation of the preoperative CT scan and a finite element discretization. And then during the surgery, we want to perform an elastic registration of this model onto the intraoperative view while the liver is being deformed. Depending on the type of surgery and on the acquisition modality, the intraoperative data can be of various types. For instance, in an open surgery, we can use an RGBT camera that acquires surface deformations of the liver, in order to build point clouds. Also, in laparoscopic surgery, we could use a stereoendoscopic camera to construct such a surface point cloud. But regardless of the imaging modality, this surface point cloud can be used to drive our simulations, and in particular the UMesh. This registration must be performed really quickly since the images are acquired at 20 Hz, leading to update times of less than 50 milliseconds. And during this small amount of time, the image processing must take place as well as the model update, which leads to predictions that must be made in less than 30 milliseconds. Let me first highlight the similarities with the previous seen breast scenario. So the input to the network is a partial surface point cloud in the two cases, with whose number of points can vary at each time step. In the liver scenario, we have an extra challenge, however, that is that the point cloud can be noisy and even sparser. So this introduces a very high variability in the input. So such a point cloud, surface point cloud, can be used to drive the U-mesh so that it produces a complete volumetric deformation of the organ that can be superimposed on the intraoperative surgical view in order to build the augmented reality. For the training data generation, we need to fulfill several requirements. So, as we have seen previously, we need to encode the displacements and the Neumann boundary conditions on the grid. So, in this case, the RGBD point cloud. We also need a nonlinear constitutive model. We do not need any patient-specific parametrization of the model, because here as well the input to the network will be a surface displacement. The patient-specific Dirichlet boundary conditions can be estimated from the preoperative CT scan, where the vena cava has probably been segmented and can be fixed. And also we need to generate random Neumann boundary conditions on the visible surface of the liver. So first, the encoding of the displacements on the grid. So we will do exactly as in the breast scenario. We will immerse the surface of the organ in a sparse grid discretization, and we will use an immerse boundary method for accurate simulations. In order to encode the RGBD point cloud on the grid, I propose here a work that it was not presented in the manuscript. This is a last-minute result, let's say. And we propose to compute a distance field in order to encode such a point cloud. So we are based on the works proposed in reference 18, and we will basically compute for each node of the grid, we will compute the distance to the closest point in the RGBD point cloud. And this produces kind of voxelized point cloud, like the image in the middle, which can be given to the network. Okay, so to generate our data, we imposed random displacements on the visible surface of the liver, and we selected a random amount of visible points in order to mimic the virtual RGBD point cloud. In total, we generated 2,000 samples, and the data generation and the training of the network took less than 5 hours, which is clinically acceptable because it can take place between the moment where the preoperative CT scan was acquired and the moment where the surgery starts. So once the network is trained, we assess it on a synthetic data set. So to compute some metrics, we embedded 10 markers in the liver, and we computed target registration errors. So in the image in the right, I show some network predictions in green compared to the finite element ground truth solution in red. And the first thing we notice is that there's a pretty good visual agreement. But a very important point here is that the network learned the surface correspondence between the liver's visible surface and the point clouds. This is an important point because it is not trivial to do it with the standard FEM approach, where we need to use iterative closest point algorithms to iteratively find this matching. So the network learned both the deformation and the surface correspondence. Overall, we had an average target registration error of 2.16 millimeters, and the prediction times are close to 3.8 milliseconds. This prediction time does not take into account the encoding of the RGBD point cloud in the grid, because as I said before, it's a last-minute result, so the codes are not optimized yet, and well, we can safely say that we will be able to accelerate these computations in the next weeks. So here we have some results on human liver, ex vivo human liver. So it's liver that was resected from a patient. We deformed it and we acquired an RGBD point cloud of its surface. And we also, so this RGBD point cloud appears in red, the red points in the image. And we also scanned the deformed state of the liver, which is represented by the gray wire frame in the image. The UMesh prediction is here displayed in red. And the first thing we can notice is that the point cloud is not only noisy, but also has some outliers. There are some points below that do not correspond to any visible part of the surface. And still the UMesh is robust to these outliers. Also in the upper lobe we can see that there is a pretty big mismatch between the two shapes. This is due to the fact that the ex vivo liver was lying on a table and the lobe was slightly going up, which was not taken into account in our training, of course, and which is not really well characterized with this point cloud. So the UMesh failed in predicting this part. But still, despite these little details, well, not details, despite these points, the UMesh still predicts a pretty good solution with 7.2 millimeter error at the lesions, which is comparable to the error obtained with the FEM used to train it, but is about 500 times faster in the prediction. But again, we exclude the voxelization part that can be a little bit long for now. The final goal of this project is to include such an augmented view in an operating room. So here in the image in the left, I show an operating room in Paul Brousse Hospital in Paris, and under the green arrow we have our RGBD camera. And well, I just wanted to show the simple setup of our setup. So the camera will continuously record the surface of the liver, and it can be continuously feeding the UMesh so that it predicts an updated view of the deformed organ. So here we have some first results that are, well, not satisfying yet, but I guess it's normal because we need to handle a lot of uncertainties and a lot of noise, and yeah, well, the processing of the RGBD point cloud is also not easy, and well, all the occlusions are also not correctly handled, and if the surgeon is putting his hand on top of the view, well, it's not amazing, and also the boundary conditions might be incorrect. So if I summarize, we can say that the UMesh is an interface between precise biomechanical finite element modeling that is not capable of real time, and clinical applications that require both high accuracy and very high speed. So our method allows for fast and accurate predictions of complex deformations of soft tissue, about 500 times faster than the reference finite element solution. One of the major strengths of our approach is the generic training that allows the method to be insensitive to patient-specific elastic properties as it imposes surface displacements, and also insensitive to Neumann boundary conditions. However, the main limitation of our approach is the heavy data generation process that needs to be done for every new geometry. Still, we saw that this is not a blocking point because it can be done before the surgery, but still is a limitation. And the other limitation is that we assumed that the Dirichlet boundary conditions were known in advance. But what happens if they are incorrect or if they change during the surgery? Well, this is where the last section comes into play. I will explain how we could include intraoperatively available information into the network. So let me first come back to the initial problem. We wanted to produce a generic deep neural network that was capable of predicting the solution to any combination of this set of problems. And we actually did it. But what happens now if the nonlinear constitutive equation is unknown or not exactly identified, and if the Dirichlet boundary conditions are unknown? Fortunately, once the surgery has started, there is a lot of information available that can be exploited to determine such unknowns. For example, the invisible organ attachment, so the Dirichlet boundary conditions, can be estimated using Bayesian filtering, and in particular the reduced order unscented Kalman filter that models the sought parameters as Gaussian probability density functions that are transformed based on observations in order to find the most likely values of the parameters. So once these parameters are identified with one of these methods, for instance, we could imagine including them in the network as an extra channel in the input. In particular, we could encode the boundary conditions as a binary mask and say with ones the areas that are fixed, and with zeros the free nodes. We could also imagine in another scenario, if we were to use forces as input, we could imagine giving the elasticity parameters as extra input that can also be estimated using Bayesian filtering. The problem with these approaches is that the bigger the number of parameters we want to sample, the bigger the amount of training data, and is some kind of a brute force solution to include, to introduce this information in the network like that. So a more subtle solution relies on the usage of transfer learning to generalize our networks. So before the surgery, we can train a generic model with average parameters, and then once the surgery has started, use Bayesian filter or neural networks specific for this kind of tasks to estimate the patient's specific boundary conditions. And the obtained boundary conditions can be used to generate new finite element data very quickly and very few data in order to refine the network. So we have some preliminary results that show that the network converges very fast as long as it was correctly initialized, and that very few data is needed. This means that all this process could take place in, let's say, 10 or 15 minutes at the beginning of the surgery. So this is an approximate amount of time because we still haven't tested, but it could work. Another point that I would like to highlight, and I will finish with that, is what happens if the constitutive model itself is incorrect and if we can estimate it from the patient-specific data. So if we found a way to acquire enough volumetric information of the inside of the organ without exposing the patient to high radiation doses, we could use this data to refine our networks with transfer learning. But, well, we don't know exactly how we could do this and how we could include the real data in our trainings. Well, so this was kind of an open question for the end. This was all from my part. Now it's time for questions, and thank you very much for your attention.
Thank you very much, Andrea, for this very clear, well illustrated and very pedagogical presentation. So the discussion is now open. I propose to start with the first reviewer, Professor José Martinguero. José, I know that you have some duties this morning, so if you want to leave the audience after your questions, please don't hesitate, and you can join us afterwards at the end of this committee. So please, the microphone is yours.
Thank you very much for your understanding. Yeah, Andrea, thank you for the presentation. It was very clear. I would like first of all to congratulate you and your supervisor because the work is very good. And it's especially remarkable that make contributions in different fields, and this is difficult sometimes because one is always a bit biased to its first field of knowledge, but you manage to make good contributions in the field of quantum mechanics, also in the field of machine deep learning. So, first of all, congratulations to the work and also for the writing of the manuscript that was excellent.
Thank you.
And then I just have a few questions or comments about the work that I would like to discuss with you. First of all, it's related to the experimental setup, because when you start working with deep learning, at the beginning you tried some fully connected, not that deep neural networks, but the thing is that you tackle the problem from the very beginning with either neural networks or more deeper neural networks, like convolutional neural networks and so on. So my question is whether you have tried or not more simple models, because sometimes you know, or you find a model that is maybe not that sophisticated, but it was reasonable well with a performance maybe not that good, but similarly you may extract more useful conclusions, it's more interpretable, it also has better generalization capabilities. So it's like a double question, whether you didn't try more simple models to see whether they were good enough. And also related to experimental setup, how have you dealt with generalization issues and with the capability of the model to work well with new data? Because I know that you have done maybe the usual stuff of splitting training, validation, and so on, but I haven't seen a very detailed discussion about how you have dealt with this topic, which is important, like avoiding overtraining, overfitting. So I would like you can clarify these issues a bit.
Okay, thank you for the question. So to answer the first part, have we tried simpler networks? So the answer is yes, we have. But it's true that we started directly with the unit. So it was like a post in a second phase where we tried using simple, fully connected layers for simulating the deformations of a beam, and it actually worked really well as well. And it could be, so such networks were trained even faster, but the problem with those is that first the extrapolation capabilities of the fully connected networks were even worse than that of the UMesh, meaning that for a sample that was not like let's say a force that was out of the range, well, not a force, but a displacement that was out of the range of the ones seen in the training, the UMesh was producing more realistic deformations, even if still incorrect, but the UMesh was more robust to this kind of things. And yeah, the second reason is because when modeling some other more complicated object than beams, the fully connected networks were not adapted. So yeah, these are the main reasons. For the second question, so how we dealt with generalization, in particular overfitting. So it is true that for this particular project of the UMesh, we did not perform any regularization of the data, because, well, we were checking the losses, of course, of both the testing and the training data, but we did not present any overfitting of the data. So we assumed that the training data was good enough and general enough to describe the targeted problem, and that the samples were sufficiently distinct, significantly distinct, the ones from the others, in order to really sample all the possible, in order to, no, not sample, but characterize, let's say, the possible range of deformations that will happen after doing a surgery, for example.
Okay, thank you. I have another double question, which is related more to next steps. I guess that you've done a lot in this doctoral work, and at some point you are paving the way with all the researchers from the field that will be very successful in the next few years in the application of this kind of deep learning approaches to this application. So as you are at some point just setting the foundations of this, I would like to know your opinion about next steps in two particular cases. One is if you think that maybe next improvements will be related to maybe more sophisticated convolutional models. For instance, I'm thinking of VNet, that I think that you even use it in your work, and it's like the natural evolution of VNet. Or maybe it's or. You think that recurrent neural networks may play a role? I have this feeling, because as you know, in recurrent neural networks, it's also a deep learning approach, but in this case, the idea is that you get the information in a temporal memory, and with this information, you are able to give good predictions, taking information of what has happened before. So thinking of not only maybe predicting the formations, but maybe predicting how the formations may evolve with time, I think recurrent neural networks might be an approach to be taken into account. And I would like to your opinion about these both possible approaches. Whether you think that next steps will be related to more sophisticated convolutional neural networks, or recurrent neural networks, or both?
Okay, this is an interesting question. I would say that it depends on the targeted applications. In my path, I think I will stick to static simulations, and in this particular case, probably improving or complexifying the convolutional networks will be the step to follow. So in particular, we've been thinking a little bit about, so instead of using standard convolutions, since we are using sparse grid discretizations, we could use an octree-like sparse grid with several subdivision layers, meaning that we would need adaptive convolutions. There is already some work done on that, but this could be one of the next steps in order to accelerate the training, because the convolutions in the outer part of the organ would be extremely quickly, and also more accurate, because the convolutions inside the organ will be well more accurate. On the other hand, if we were to do dynamics, which again is probably not my objective in the next future, I completely agree that recurrent neural networks are the way to go because of all what you said. I think there is somebody in our team that is working on that. Well, at least at some point he tried, and he had this idea of using recurrent neural networks to account for the time evolution of the networks. But yeah, again, it's not really the targeted applications for it. We don't hear you, Jose.
Sorry, I was with some. Thank you for your answer. I just have two more questions or comments. One is related to the patient-specific simulation, which is one of the most valuable parts of the thesis, in my opinion, because it's very close to the real application. In this part, maybe because it's not my field of expertise, I would like just if you can summarize for me your main contributions there, because in some parts, some of the chapters maybe were a bit short, maybe for me, because I'm not that expert there. So, for instance, chapter 5, when I finished chapter 5, I didn't have a very clear idea of what you really did or what you really took from other authors and so on. So, I would, if you can just summarize a bit your main contributions in this part of the thesis.
Yeah, sure. Sure. It was so this chapter related to patient-specific properties, and in particular the Bayesian filtering part, was shorter than the others in purpose, because indeed this is not my work. So other members of our team have worked on these subjects. So the estimation of the boundary conditions of the liver was completely done by some other persons, but the estimation of the Young's modulus on the synthetic liver, this I did it together with these other persons in the team. So that's why I didn't want to make a very big part about it. But still, I found it important to have it because it could very precisely answer to these questions of how to introduce this data with transfer learning. So yeah, that's the main reason why. But also in the part, well, in this project of the sclera that I didn't present in the presentation due to a lack of time, I did myself the assimilation process to estimate the boundary conditions of not the boundary conditions, sorry, the stiffness of the sclera by using this Bayesian filtering. And yeah, well, this was an important point actually to make that method usable in real clinical setups. But yeah, this was my main contribution in this topic, because it was done with real data, etc. The other one with the liver, yeah, was on synthetic data or not mine.
Okay, thank you. And just to finish, because the thesis is very good, we need to be sometimes a little critical with ourselves. So I would like to know, in your opinion, the main limitation of your work. I think, just to give you some clues, maybe for instance in chapter 7 you only give deal with one liver, so maybe one possible extension of the work might be to increase the size of the data sets and then therefore the representativity and so on. But I would like to know your opinion about the main work and which solution might be adequate to solve it.
Yeah, of course. So it's true that in that chapter we only validated on one lever for the ex vivo part, but in the in vivo part, which is not working really well yet, but it was another lever. So it was two different trainings, two different networks. But so now I have started working with these surgeons in Paris from the image I showed, and we are acquiring more and more data, specifically to validate the approach on more levers. The limitation that I see with that is that for every new lever, we need to retrain our network with the patient-specific geometry, and well, it's not like a material limitation, but it's not, let's say, fluid. It would be, I would prefer, and I guess the surgeons as well, to have a network that is ready and just clicking on a button or somewhere, and it works for any lever. This means that we could take into account the geometry, for instance, of the organ. Yeah. Some other. Yeah, I got. No. There are some other limitations. I was just thinking. Of course, I need, like, the next step is really improve the in vivo part. So I could, for example, well, of course, improve all the data acquisition part with the RGBD camera, but I could also make the network robust to more inconvenience of the RGBD point cloud. For example, I could make the network handle occlusions, for instance, and that way it would be way more robust during the surgeries. And of course, improve accelerate this encoding of the RGBD point cloud in the grid. This is like the very, very next step.
Okay, thank you, Andrea. So thank you very much for all the good answers that were very clear. You have demonstrated your capacity to keep, in this case, the work, really knowledge of the work you've done. I mean, which is absolutely fantastic. I mean, I was very grateful to read it and to be up to date of your work. And just to congratulate once again you and the supervision for the excellent research you've done, and encourage you to carry on in the next years, improving it now as a doctoral researcher in that hopefully tomorrow. So thank you.
Thank you very much.
Thank you very much, Jose and Andrea, for this very interesting presentation. I propose now to move to the second reviewer, so Professor Elias Cuito from the Universitat de Zaragoza. So please, Elias.
Thank you so much, Ivan. Well, thank you also to you and your advisor, to Stefan, for having invited me to be here today, well, here, at least virtually. And congratulations for your very nice work. I think that your thesis opens a very interesting line of research in our community that for sure will involve many groups in the near future, including mine, of course. We are very interested in this field, and I think that your thesis opens this line, as I said before, in a very elegant way. So congratulations for the thesis, for the work, and also for the very didactic pedagogic exposition you have just made. Well, I have some questions that arise nevertheless from curiosity and from the desire to know more of the details of the thesis. So, well, to begin with, first of all, at the very beginning, the title of your thesis, you said that your work is the type of network you develop is physics-based, and I think this is a little bit, I won't say confusion, but why do you say that it is physics-based? Because in the community, I think that by indicating physics-based or physics-informed, probably they are not the same, physics-based and physics-informed networks. But is there any constraint on the physics of the results, or there is only physics on the entry side of the network? I mean, you are feeding the network with results coming from physical simulations, but do you enforce somehow the physical meaning of the results? Don't you fear that as many networks produce sometimes a non-physical result could appear as a result of this type of architecture?
I see that point. Thank you for pointing it out. So I do not encode specifically any physics of the problem in the network. So it's not physics informed, but I agree that it might deal to confusion. So the only part where, so we chose physics-based because still, even if we're not encoding anything hardly in the network, then the data comes from simulations, from finite element simulation. So it was a way to, actually, without the terminology employed by the PINs, so these physics-informed neural networks, even the term physics-informed neural network would have been interesting for our application, because it's the case, like the network is informed with some physical inputs. So we wanted something that was similar but not the same, trying to avoid confusion, but yeah, well, it seems that we fail in avoiding confusion, but what?
No, it's perfect. No problem. Just to clarify things. Second question. At the very beginning of your presentation, you showed the equilibrium equation for solid mechanics, and you said I'm trying to solve this equation. But you showed the equation in a small strain framework. But if I didn't understand well, finally you solved large strain problems, didn't you?
Yeah, I did. So here it was only for the clarity of the equations, and yeah, I agree that it's limited to the small strains, this equation. But yeah, indeed, I tried it with large strains, and not only with the hyperelastic Saint-Venant, we also tried training the network with the neo-Hookean material, which is really a non-linear material, and it also works. So yeah, this was a simplification.
Okay. That's clear. Well, later on your talk, you mentioned very briefly graph networks, and you mentioned that the performance of graph networks was not that good according to your
Well, we didn't found an available implementation that we could use easily and quickly. That is the main reason. So yeah, maybe performance issues was too strong, and it wasn't maybe not related to the method itself, but more to the availability of its usage in an easy and quick manner in our approaches. So yeah, that's the main reason. But it would be actually very interesting to look into that, because if we want to change the network, we could imagine working with something completely different.
Okay. Perfect. So we have room for research.
Definitely.
That side of the. Well, and finally, just to clarify things, because well, the first part of your presentation was devoted, so to speak, to the forward problem. You apply loads to your liver, say, or breast, and your network provides you with the displacement field and stresses, strain, etc. But at the second part of the thesis, you need to solve the inverse problem, in the sense that you have a partial view of your organ that you have to register with your model, and you have in principle no information about the particular position of the load. You need to infer the position of the load and still provide with the displacement field. So I think I haven't been able to understand very well how do you perform all these steps in the so to speak inverse program. How do you register your model with the image coming from the camera in the operating room, provided that usually you don't have anything more than a partial view of your organ, and how do you determine the position of the load for that situation?
Okay, thank you for the question. So in open surgery, that is the surgery we're working with, at least for now, pretty large, well, like 30%, or yeah, about 30% of the surface is visible, meaning that we can see more than only one lobe. And on the results that I've shown, like the two levers that we've worked on, we have very good access to the surface, to the what we call the visible surface. So during the training of the network, we sampled all these visible surface. So the network learns that this is the part that will be that is potentially visible during the surgery. So it knows that it needs to match somehow the point cloud that he will have, that he will receive, with all this part of surface. We could, of course, increase or reduce this visible surface to make it more robust, but yeah, the network learns to do this matching, but again, not again. I didn't say it. We assume that the point cloud that we give to the network is already rigidly registered into the reference frame of the liver. Yeah, sorry, I didn't get that point. This was the question. So yeah, sorry, no, it was not. Actually, it was not that far from the deformed surface. Yeah.
That's perfect. That clarifies it a lot. Well, thank you so much. Thank you for your presentation. Thank you for your clear answers to my questions. Thank you, thank you. So, first of all, excellent work. I mean, it's excellent work. I really enjoyed reading your thesis, and thank you for inviting me. And obviously, congratulations to you and your supervisor. So, I have like 3-4 questions. Some of the questions you already answered actually, which he has asked actually. So, I will be skipping those questions. So, first is, so while reading your thesis, one thing actually confused me. So, sometimes you are using unit, which is well known in the deep learning community, and then you are using UMS. So I got the feeling that both are same, but I would like you to elaborate on that there is some differences in the two things, UNet and UMS.
Okay.
So
So UNet is, you're correct, so it's the name of the architecture, and UMesh is what I call the whole process of training the unit with finite element data encoded in a regular grid mesh. That's why UMesh. So yeah, UMesh is the whole process.
I got the feeling before the better explained. So okay, moving on. And so in chapter 6 of the thesis, we can see what presented. So we carried out some work on two things, right? It was estimated force and using neural network. And that was, if I'm not wrong, was a classification problem based on images. Now you're surprised that since my input is image, why will I not use CNN convolution and instead use a fully connected network, because that is what you did. So some reason behind that CNN did not work.
I am sorry. I'm not sure if I understood what you said. Can you like repeat it maybe slowlier, or please?
Yeah. No problem. In chapter 6 of your thesis, you carried out some work on force estimation, right?
Yeah, chapter 6. Okay. Yeah.
And that was a classification problem. Like you have image, and you were trying to find out which class of force, but you did not use CNN, which is what we need for image.
Exactly.
And instead you used a fully connected network. So I got confused. Did you try this not work or anything?
Okay, that's a good question. Thank you for repeating. Yeah, so in this Clara project for estimating forces in robotized intravitreal injections, we used a fully connected layer because, well, this was the very beginning of my PhD, where I didn't know almost anything about neural networks, and the idea was to try the simplest architecture for a problem that was not that easy to solve, but we tried the simplest thing we could find in order to understand what was going on, and it worked. So we didn't need to move on to convolutions. Of course, if I had to do this work again, I would use convolutions. It will be much faster and, well, yeah, easier actually to set up. Not faster to train, but easier to deal with that problem. So yeah, there's no specific reasoning behind that decision.
Thank you for your answer.
Yep.
And then on, so I was in the liver problem, I think your grid was 16 cross 15 cross 16, right? That was the grid you were using for the CNN.
Yeah.
So, so if I have a more difficult problem, how does it scale if I increase that grid?
Okay, this is a very interesting question. We tried it also on a 32 by 32 by 32 grid, so a cube, and the prediction times are still equal to, well, around 3 milliseconds. Despite, well, the little detail here is that the voxelization will take even longer for finer grids. But again, I don't want to take this too much into account because I will optimize it. So I don't really have an answer for this part. But for the unit prediction, it scales really well. Like the constant amount of time for the prediction, and well, if we refine the grid and we have enough training data, of course, the accuracy is even better.
Thank you. Last question. And this is on transfer learning, probably with your teammates there. So, in transfer learning, what we generally do is, in the transfer learning stage, we freeze the weights of the initial layers and only allow the last layers, like last few layers, to update.
Yep.
But this information was not well said in your thesis, so did you do the same thing, or you did something?
So, no, I didn't. I refined the entire network. I didn't. So yeah, now I know that it's more common to freeze the first layers, but when I did that work, I was not aware of that. So this could even accelerate. This would accelerate even more the training. So yeah. When I understood that, I thought, okay, this is a good news. We can simply say that we can be optimistic about this subject.
Thank you. And okay, physics-based, you have already answered. Geometric learning, you have already answered. So that's it from my end. Congratulations again, and thank you, and excellent work.
Thank you very much. I just wanted to add something I thought about. Elias, you asked me about this physics-based term. I would like to add that there is also somebody in the team that tried to use the network as a predictor for the initial guess for a Newton solver. So to initialize the Newton static solver with the network prediction. And in that case, it would maybe not introduce physics in the network, but all the pipeline could be more physics-based. It was just to add this point, if it clarifies a little bit further.
That's a very nice idea, indeed. And I see that you are able to think in parallel, answering one referee while thinking at the same time on the questions of the others. Excellent. Thank you for your answer.
You're welcome.
Okay, thank you, Andrea, for this panel discussion, and thank you for your question. I won't go into details of questions because of these communication difficulties, and because as I said in my introduction, I already had the opportunity to interact with you, and you are during your PhD individual monitoring committee. I just wanted to say, like all the other members, that I really appreciated your manuscript, as well as your clear presentation you gave today in front of this committee. So thank you for that. So I propose to finish with your supervisor, Stefan. So he's not on the scene. Stefan, if you will go with Andrea to say some words, or what do you prefer?
I think I can try this microphone. I don't know if you can hear me. It works? Okay, so you don't see me because I don't know how to turn on the camera, but I think that will do. So, very first thing I want to say is how grateful I am for you, members of the committee, to be somehow with us today. And really, I say this truthfully because I know that some of you have very challenging things to deal with, and we're really grateful with Andrea that you're with us today. Of course, it would have been nicer to have you here in Strasbourg, and and discuss and have a good meal, but maybe, again, this is something we can do because one of the things that clearly appear for the discussions is that they are very interesting topics of interest that we should discuss more in depth, and hopefully we can do this next year when things get a bit easier to deal with. But okay, today is your day, Andrea, okay? It's your PhD defense, and been talking about it for a while now, and as everybody, I'm really proud to see you here. I mean, I love these days, so I like that, and I guess everybody said that we all can witness how much work you've done in only 3 years. I think it's also important to remember that, because I know that in different countries, PhDs can last 4 or 5 years, and you really started only 3 years ago, and you've done quite a lot. And when you started, I had some sort of a plan, a bit more of a crazy idea, and I had no idea if it would work out, but you made it somehow look like it was not an impossible mission, and you really managed to make your PhD a success story, and I think everybody here said that. I mean, in a way, with that work you've opened a little but important door in the field of computational biomechanics. I think there are cool things to look into or look through that door. And we didn't say that, but you also had, I mean, very good publications. You had 2 oral talks at MITAI, which doesn't happen so often. So you've been a productive researcher, and in a way, although it's a bit of a pity that we cannot have a normal PhD defense here, I think that if I remember last year in Shenzhen with about 2,000 people in the room, sort of balances things out. So again, you had your share of people listening to you. But the last thing I want to say is, of course, that aside of being a good researcher, you're also our office gardener, party organizer, natural medicine expert, and more importantly, at least to me, a very good cake and pie baker. So please don't give up with these skills. But to conclude, and for all I would say these contributions in the large sense, so I want to thank you, of course, very much. Wish you the best for the next steps. And at least I know that you'll be near us for the next 3 months, so that's great. I know there are some people in Paris who are waiting to see some new results, but again, in the meantime, while we finish the defense today, I think you need also some good rest, and then we'll talk more about science later. Thanks again, Andrea.
Thank you.
Okay, thank you very much for Stefan. So we're supposed now inside the jury to have a short discussion before coming back to Andrea. So should we stay, Stefan, on this same platform, Scotland?
I think yes. What we'll do is, because we have our own separate video system, so we will stop the feed to YouTube, have our meeting here in the room, and then resume back, I think, in 15-20 minutes. So yeah, we stay, please all committee members stay online.
Let us know as soon as
stressée qu'au début.
So we're all set, so John, whenever you're ready.
Okay, just a few words in French to start, and then I will move to English back. Andrea, je suis vraiment désolé de ne pas pouvoir être en visuel avec vous, au téléphone, désolé pour ces conditions. J'aurais vraiment aimé au moins vous voir physiquement pour cette discussion finale. So back to English. So Andrea, the jury has clearly said that you made a very clear, well illustrated and very pedagogical presentation of your research work. The committee, the jury committee wishes to underline the broad scientific spectrum covered by your research work. From biomechanical modeling to deep neural network, including data-driven simulation of augmented surgery. You have carried out an enormous amount of research work. You have demonstrated a very high level of scientific maturity. Actually, the scientific committee has already recognized the excellence of this work with many articles that have been published or are currently being reviewed in main peer-reviewed journals in our field. So the exchange with this jury covered many aspects of your work, and you provided relevant, very well argued and convincing answers to many questions, which underline your great mastery of your research topics. As Elias Saqueto said, you already projected yourself into the future with very promising perspective from a scientific and clinical point of view, and which opens very interesting line of research that will involve many groups in the world in the future. So the conclusion of the results, the jury unanimous provide you the PhD degrees of Strasbourg University. Congratulations, Andrea.
Thank you. Thank you very much. Sorry? Thank you to all of you for being here, even if virtually you're here, you're present. That's it. That's done. Wow. No, really, I'm very happy to have done this PhD, which was really not sure actually that I was going to do it. Thank you, Stefan, for kind of convincing me to do it. Without you, I would have probably still be lost somewhere in the Amazonian forest in South America, and now I'm having a PhD, so thank you for that, and well, thank you for sharing your passion for research. This was amazing, and thank you, Jean-Nicolas, for all these things that you're doing, for all the streaming and for all the help. And thank you, Leonora, for being here. I'm very happy. I would like to just say that how do you say that in English? I dedicate this work to my grandmother that is not with us physically anymore, but I know that she's here, so Amoni, esto es para ti. Es hecho para ti este doctorado, así que bueno, I hope you enjoyed, and at least as much as I did. So thank you very much, and hope to keep on discussing with you in the near future for next exciting science. Thank you very much.